So in the previous lecture, we were doing this question, and I want to give you a method to solve this question. Let me just wait for people to join in, and then I shall elaborate. Okay. So probably this question I have given you, and I understand that this question is quite difficult for you. So I'll give you a certain suggestion to do such questions. Okay. So you can take it as a tip right now to do these questions. So this is something that we'll study in definite integral later on. But because this question has been this question popped up, so since it popped up, so I have to do it right now. Okay. So if you see the structure of this question, how does it look like? It looks as if it is limit k tends to infinity, and then I should write limit r equals to 1 to k. Just keep an eye over it. E raised to power r by k divided by k square. If you clearly see, this is how it is. And you can place r also here, right? See, if r is equal to 2, this is e ki power 2 by k. If r equal to 3, this is e ki power 3 by k. If r is equal to k, if I write k here, and if I write k square here, is that clear? So instead of the last one, if you want to write k, I will write no, it's k upon k square. Is that clear?
Yes.
Okay. So whenever you have this kind of, if you want to take a limit of a sum, and it is arranged in a manner where you can express your limit of a sum in this way. R is varying from, let's say, 1 to some point, let's say n, and limit n is tending to infinity. Then in these scenarios, what you can do, you can write your r by k as x, you can write 1 upon k as dx, and you can replace this sum by integration. You can replace this sum by integration. This is one working rule right now I'm telling you. Okay. One of the working rules which I'm telling you right now. Working rule to solve such a problem. Okay. Because actually I gave you this question, so that's why I'm doing this. So I'll do a few more questions in this pattern. Okay, then we'll end up this class. Okay. So whenever you are, whenever you have such kind of problems, you can do this. So whenever you have this some kind of questions and if it is given to you, you just try to write it in summation form. So you'll find that, okay, can I not write it in this fashion? R equals to 1 to k. And if I separately write r by k here and separately write e raised to power r by k and divided by 1 upon k, divided by k. Is that fine?
Yes.
Okay. So this is how you can do these questions. So I told you, you have to replace your 1 by k by dx. So I've replaced 1 by k as dx. And you have to replace r by k as x. So instead of r by k, I'm writing simply x. And instead of integration, instead of summation, I'm writing integration. Now you will be saying that, okay, you're replacing your summation by integration. Now you will ask, what about limits? Isn't it? Now you'll be prompted to ask, what about limits? So you see the lower limit, x is given by 1 upon k, and the upper limit x is given by k upon k. See, r upon k is equals to x only, no? So lower limit of x will be 1 upon k, the upper limit would be k upon k, as k tends to infinity. So your lower limit would be x equal to 0 and upper limit would be x equal to. So I'll write x equal to 0 here and I will write x equal to 1 here. Is that clear?
Yes.
And if I want to integrate this stuff, what I'll get? I'll simply get, you know, integration by parts.
सिर्फ फिजिक्स में पढ़ा था थोड़ा सा बस उतना ही.
Okay. So चलो मैं बता देता हूँ. So if I want to integrate such things, always remember that one part I have to keep it as it is, and another part I have to integrate it. So what I'll do, I'll write a formula for you. So fx gx, this integration, this will come out as fx integration gx minus integration f dash integration g and this entire dx. So what I'll do, I'll choose this as first function, this as second function, whichever is integrable. So I'll use it as a second function. You know that if I use x here, so it will integrate and become x square, but it will become x square. And further, if I keep on integrating, the powers would keep on increasing. So the better way is to take gx as e to the power x. And lately, you will also understand that there is a rule called as ILIT. It is not as such rule, but okay, but this is how we take preference. So this is the order of preference for your uh, integrable function. So uh, since you know that your inverse, I don't know the for f of x, I think. So if you want to integrate this thing, what I'll do, I'll integrate e to the power x. So I'll use e to the power x as gx, and then I'll whenever you're going to do integration again, you'll be able to understand what I'm doing. But right now, you choose your fx as x and you choose your gx as e to the power x. So x as it is, integration gx would become integration e to the power x minus integration the derivative of f. What is f? It is x. The derivative of x is 1. Integration of g again. Is that fine?
Yes.
Okay, this is simply your integral by parts. From where to where? From 0 to 1. If you put 1 here, this will become e minus e. And if you put 0 here, it will become 0 minus e to the power 0. So your answer would come out as 1. Because this will become 0 and 0 minus of minus 1, this will become 1. Is that clear?
Yes.
Okay. Now let us move to something called as we'll do a few more questions of this sort, but I would do them later on because like, there are many questions to do now. Okay, is that fine? Or I would do some questions actually come to the continuity as well. Let us do a few more questions on limits so that now you'll be able to understand what I want to convey. Okay, is that fine now? ये चीज समझ में आ गई यहाँ तक? Okay.
हाँ
अब एक काम करो, try to do this. Try to do this. Find me the value of limit. So how would you do it? So I'll write in very compact sense, I'll write limit n tends to infinity. This is summation k equal to 0 to n minus 1. See, and this is e raised to power k upon n. If you find it, if you can see what I want to say. See, place k equal to 0. This will be e to the power 0. This is 1. Here it is. You place k equal to 1. This is e to the power 1 upon n. Here it is. You place k equal to 2, e to the power 2 upon n. And you place k equal to n minus 1. This is e to the power n minus 1 upon n. And all of these 1 upon n you can multiply. Is that clear?
Yes.
And your limit is on n. So I told you whenever you have such form, you write 1 upon n as dx. You write e to the power r upon n or your k upon n as simply x. And since you've replaced your x by k upon n, so what would be the lower limit? The lower limit would be 0 because lower limit k is equal to 0. And upper limit x is equal to n minus 1 upon n as n tends to infinity. So this limit would become 1. This is simply integration from 0 to 1 e to the power x. What is e to the power x integral? E to the power x integral is e to the power x from 0 to 1. This you'll get e to the power 1 minus 1. So answer would be e minus 1. Is that clear?
Yes, sir.
Okay, so such are the questions. Such questions you will be asked in examination. Okay, so इस तरह के questions exam में आते रहते हैं. Uh, I hope you will be able to get those questions. Okay. Uh, Now let us move to continuous functions. Okay, now let us move to continuous functions. Now let us move to continuous functions. Okay, so one thing that continuity is an important property. Continuity, in very general sense, you can say that if I say that my function is continuous, one of the very vague way of saying it can be to say that if I am able to make the graph of that particular function without picking my hand up, okay, without picking my hand up, that would be a continuous function. But this is a very vague or very abstract kind of definition. So without, let's say, if I have to make the graph of this particular function, obviously in order to make this graph, I will make this graph from here to here, and then I will have to pick my hand up. Only then I can continue from here. So clearly this is discontinuous at this point. So like again, I told you this is quite abstract or vague way of not vague as such, but abstract way of saying what is continuous function. Okay. Now what will be more elaborate thing to say? I'll say that my function, if a function is continuous, if a function is continuous at point P, at point, let's say x equal to P, then the first thing is that limit x tends to P must exist. And if it exists, then this is equivalent to writing the value of function at that point. So first thing that is absolute necessary for a function to be continuous is that your function should be defined at that particular point. And always remember that it is a local property, in the sense I will always say about a point. I'll always say whether your function is continuous at a point. And let's say you have a set A, let's say A comma B. At every point your function is continuous, then I will say that my function is continuous on set A. But always remember, whenever I'm talking about continuity, I'll be talking about continuity at a point. So if I say that my function is continuous at a point, then limit x tends to that particular point, let's say P, that particular limit should exist, and it should be equal to the value of the function at that point. And if you correctly remember, I gave you the very first limit to be evaluated. This was the function. And you can clearly see that your function is not defined at x equal to 2. And so therefore, whenever I was formulating the definition for limits, then epsilon del definition to limits, I was saying that your function should be defined in the deleted neighborhood of x equal to 2. That is, except at x equal to 2, your function is defined. But here, when I'm talking about continuity, my function should be defined at that particular point. Because if function is not defined at that point, at that particular point, then at that particular point, your function will never be continuous. Is that clear? So for a function to be continuous, for a function to be continuous at point x equal to 3, function must be defined at that point. Because if function is not defined at x equal to p, then function cannot be continuous at x equal to p. Is that clear?
Yes, sir.
Okay. Okay. This is point number 1. The second point that I need to mention is, so let's say if I say, what about fx equal to 1 over x? So even before I make the graph, so as x tends to 0, your 1 upon x would go towards infinity, and as x tends to 0 minus, your x would go towards minus infinity. So even if I don't make the graph, you are tempted to write, okay, this function is discontinuous at x equal to 0. Why do you say so? Because you already know that at x equal to 0, you can see that your function is discontinuous. That is one. Another thing that you know that at x equal to 0 is your function is not defined. Since your function is not defined at a point, then your function will be discontinuous at that particular point. Okay. And further, if I want to elaborate this, and if I want to write it for a set, so I'll write a function is said to be continuous on a domain D, which is a subset of R, if it is continuous at each point of the domain D. Is that clear?
Yes,
Is
sir.
that okay? Now let us come to algebra of continuous functions, and I'll write it in one go only. I'll not explain you right now why I'm doing that, but that I'll do for you. Okay. Always remember that if f and g are two continuous functions on a common domain D, okay, on the common domain D means where both of them are simultaneously defined. If they're not simultaneously defined, let's say this is defined at D1 and let's say this is defined at D2, then the common domain would infer to the intersection of D1 and D2. Is that clear? Because some function can only be defined in the common domain. Is that clear? Let
Yes,
f
sir.
and c are two continuous functions on a common domain D, where D is D1 intersection D2 and k be a real number. Then f plus minus g, k times f into g, and f divided by g, provided g is not equal to 0, are all continuous functions. This is what is referred to as algebra of continuous functions. Is that clear?
Yes, sir.
Okay, so now let us do a problem and then we'll take a break and then we'll resume our class today. Is that clear?
Yes.
Okay. So let us do a question. Then I think that was a very beautiful question from JEE exam. I'll do that question. That is a difficult question, no doubt. But I hope you'll be able to get it, and then we'll do easier ones also. But let us do a good question first. So this was, I think, asked in JEE exam 2004. Okay. So if f is defined from -1 to 1 to r, okay, I think this is something that you will not be able to do right now. Okay, you will not be able to do right now. So a simple question correct. I think this will be quite difficult for you to do right now. Let us do a simple question at first, and then we'll move to difficult ones. Okay. Okay. So continuity, I think again there will be a continuity and differentiability question. So I want to give you a pure continuity question at first. Okay. Then we'll move on to differentiability. Just give me a minute. Okay. Which of the following function has finite number of discontinuity? Which of the following function has finite number of discontinuity? Finite. Option number A, tangent x. Option number B, x into greatest integer of x. Option number C, modulus of x divided by x. And option number D, sine greatest integer n by x. So I'll make the graph for you. Okay. So I told you at the very first instance that for a function to be continuous, it should be well defined at that particular point. So if you want to write tan x is what? It is equals to sin x upon cosine x. Is that clear? Where your tan x is not defined. So your tan x is not defined at all those points where cosine x is 0. And cosine x is 0 for what all x? It is 0 for 2n plus 1 pi by 2. Is that clear? Harshad, is that clear?
Yes, sir.
It means what? It means that at all these points, your tan x must be discontinuous. Okay, and this is something that you can verify from graph also. At 2n plus 1 pi by 2, where n belongs to z. So if your n belongs to z, so how many points are these? There would be infinitely many points because there are infinitely many integers. So there are infinitely many discontinuities for tan x. Is that clear?
Yes, sir.
So this cannot be the case. Forget about it. If you want to draw the graph also, I can draw that for you. So for example, I'm just drawing it right now, then we'll elaborate it when we'll do the curve sketching thing. But right now, let's say at x equal to pi by 2, at x equal to 3 pi by 2, at x equal to 5 pi by 2, so on and so forth. So this is your pi by 2. This is, let's say, 3 pi by 2. This is, let's say, pi by 2. This is your 0. This is, let's say, your minus pi by 2. This is your minus 3 pi by 2, so on and so forth. So your tan x, as x tends to minus pi by 2, it tends towards minus infinity. Then at 0, it becomes 0. And at x tends to pi by 2, it will become infinity.
Yes, sir.
X tends to pi by 2 plus. So pi by 2 plus means what? Pi by 2 plus means limit h tends to 0, tan of pi by 2 plus h. And it will be cotangent h and with a negative sign because of the second quadrant, your tan x is negative. So it will become minus infinity. So it will again start from here. It will again start from here. It will intersect at pi and then it will be like this. Is that clear?
Yes.
Again, it will start from here. Again, it will intersect at 2 pi and this is it. So you can clearly see this is discontinuous at 2n plus 1 pi by 2s. So it is clearly discontinuous at 2n plus 1 pi by 2, where n belongs to z. Is that clear? So you can see that these are how many discontinuities? These are infinitely many discontinuities. Similarly, you see greatest integer x is written here also and greatest integer x is written also here. And you know that your greatest integer x is discontinuous at all integral points. If you correctly remember that if I want to draw the graph of greatest integer from x equal to 0 to 1, the graph is like this. Exactly at x equal to 1, your graph becomes this. From 1 to 2, again it is 1. At 2, it becomes 2. From 2 to 3, it becomes 2. At x equal to 3 to 4, it will become this. So this is how it is. So you can clearly see that it is continuous at integers, isn't it?
Yes, sir.
Do I need to elaborate this? I mean,
No, sir, I got it.
you got my point now. So your greatest integer x is discontinuous at all these points.
Yes, sir.
So if I want to write what is x into greatest integer of x, so I will have to divide. Let's say I'm dividing on the positive side only. On the negative side, the same can be done. From x equal to 0 to 1, it is 0. 0 into anything is 0. From x equal to 1 to 2, sorry, x equal to 1 to 2, it will be simply equals to x because your greatest integer x would become 1. Is that clear? From x, from 2 to 3, it will become 2x. From x 3 to 4, it will become 3x, so on and so forth. Is that clear?
Yes, sir.
देखो ये जो greatest integer है, it will become integral. It will hold an integral value. So let's say if x lies between 0 and 1, it will become 0. If x lies between 1 and 2, it will become 1. So 1 into x is 1, so on and so forth. And now if you want to evaluate limit, so let's say if I want to evaluate limit at x equal to 1, so towards the right, the limit is 1, and towards the left, limit is 0. Towards the right, the limit is 4 here, 2 plus h. So 2 into 2 plus h is 4. And to the left, x 2 minus, it will become simply 2. So you can find that this particular function is discontinuous at all x belongs to integers. And how many integers are there? In totality, infinite. So there will be infinitely many discontinuities. Is that clear?
Yes.
Okay. And similarly, I'm leaving this as a homework to you, and we'll discuss this tomorrow. This will also be discontinuous at infinitely many points. What about this particular function? This particular function is at times referred to as signum function or sine function. Okay, this is at times referred to as signum function or sine function. Why it is said so? See, modulus of x divided by x. So if your x is positive, your modulus of x will become x. So modulus of x upon x will give you 1. So for positive value, you have a sine 1. So this is signum function. At times नहीं इसको signum function बोलते हैं. क्या बोलते हैं? Signum function. So always remember modulus of x divided by x is referred to as signum function or sine function, SGN function. What does it return? It returns either 1 or -1. खुद सोचो, अगर x नेगेटिव है तो modulus of x क्या बोलोगे? -1, -x. So -x upon x would be -1. And whenever x is greater than 0, then modulus of x would be x upon x is 1. Is that clear?
Yes,
So
sir.
what does it return? It returns the sign of the function. So for example, if it is positive, it will return 1. And if x is negative, then mod of x will become -x. It will return you -1. So it points out the sign. So if I'm saying the signum function of x is -1, I'm referring to an input which is negative. If I'm referring that my signum function is +1, then I'm referring that whatever input is there in the signum, it is positive. So you can see that this particular function suffers a discontinuity at x equal to 0, because at x equal to 0, it is not defined. And so clearly, there is only one point of discontinuity, which is x equal to 0 here. If one wants to ask what is the jump of discontinuity, the jump of discontinuity in this case is 2. So jump of discontinuity is 2. So as x tends to 0 plus, your function would fluctuate here, would go towards 1. And if x is 0 minus, then it will come at -1. So clearly at x equal to 0, there is a discontinuity. Otherwise, function is 1. 1 is a constant function. Otherwise, function is -1. -1 is also a constant function. So here you have only finite. In fact, you have only one discontinuous point. Okay, so you have only one point of discontinuity. So your answer should be that which of the following function has a finite number of discontinuity? The answer should be C. Is that clear?
Yes, sir.
This again, if you want to evaluate, again the same process, only one needs to, because greatest integer x is discontinuous at integers, and there are infinitely many integers. So again, this will also have discontinuity at infinite number of points. Okay.
Yes, sir.
So I hope this session made sense to you, and we'll continue all these things tomorrow. So tomorrow, probably day after, we'll finish off with maths, and then we'll start something of physics. Okay.
Yes, sir.
Okay, better. Bye bye.
Thank you, sir.
Okay.